Hello, everyone. Today we're going to talk about measure of relative standing and box plots. So a definition we'll use a lot in this class is what's called a z-score. A z-score is the number of standard deviations that a given value x is above or below the mean. So to compute the z-score, if we want to do it by hand, z is equal to x, so the value, minus the mean, divided by the standard deviation. And if it's a population, same thing. Instead of x bar and s, we'll use mu and sigma. And we're going to round z-scores to 2 decimal places. And we'll see why a little bit later on. But a lot of times we'll use technology as well to find these z-scores. Some properties of z-scores. A z-score is the number of standard deviations that a given value x is above or below the mean. Scores have no unit of measurement. So they'll always just be a number, and we're typically going to have two decimal points. Using the same range rule of thumb, a data value is significantly low if it is less than or equal to -2, or the value is significantly high if the z-score is greater than or equal to 2. So -2 represents the value that is exactly 2 standard deviations below the mean. The number 2 represents the value that is exactly 2 standard deviations above the mean. So -2 below, 2 above. If the data value is less than the mean, the z-score is negative. So we will have negative numbers with z-score. So let's look at an example. Which of the following 2 data values is more extreme relative to the data set which it came from? So, first example, 99 degrees Fahrenheit temperature of an adult among 106 adults with the sample mean of 98.2 and sample standard deviation of 0.62, or the weight 5.7790 grams of a quarter among 40 quarters with sample mean 5.63930 and sample standard deviation 0.06194. So we're going to take the value, subtract from the mean, and divide by standard deviation. Whichever one has a larger z-score, well, once we take the absolute value if something's negative, is going to be more extreme. So let's take a look. So in our first example, if I take the value, which was 99 degrees Fahrenheit, so I'm taking 99 degrees Fahrenheit, subtracting it from the mean, and dividing it by the standard deviation, so 99 minus 98.2, and then divided by 0.62, I'd get a z-score of 1.29. If I look at the second example, 5.779 minus the mean divided by the standard deviation, we would get a z-score of 2.26. These are both positive, so it's easy to see which one's further away from the mean. So since 2.26 is larger than 1.29, it is more of an extreme value. So let's say it was negative 2.26. Say we break this out and we get negative 2.26 as our z-score. It would still be a larger of or it still would be more of an extreme value because it's still further away from the mean, even though it's negative. It's easier to see if they're both positive because 2 is bigger than 1, so it's going to be the more extreme value. But it is the absolute value of the numbers anyways. So we also are going to use what are called percentiles. Percentiles are measures of location, denoted P1, P2, P99, meaning P1 is the first percentile, P2 is the second percentile, P99 would be the 99th percentile, and then everything in between. So these percentiles divide a set of data range into 100 groups. So 1% of values are going to fall into each group. So the 99th percentile is the 99th group, which means you're the 1% of data values will fall in that 99th percentile. So to calculate these values, we're going to use this following formula. So we're going to take the number of values less than x and then divide it by the total number of values, and we multiply then by 100. So number of values less than the value, divide by the total number of values, multiply by 100. All right, so let's take a look here. Let's find the percentile for the wait time of 45 minutes. So pause the video and give this a try. Count up the number of values. Doesn't matter what the values are, just count up the number of values that are less than 45. So 1, 2, 3, 4, 5, 6. Just keep counting. All the ones less than 45. So all of these values would be included. Count all of them up. That would be my numerator. So however many values I just circled, and we're going to divide it by the total number of values, and then multiply by 100. So pause it and give it a try. So the percentile of 45, I circled, I should have circled 36 numbers. So that's where this 36 comes from. And then there's 50 in total. So we do 36 divided by 50, and then we're going to multiply by 100th. We get 72, which means it'd be in the 72nd percentile. So to summarize this, we'd say a wait time of 45 minutes is in the 72nd percentile. This can be interpreted loosely as this. A wait time of 45 minutes separates the lowest 72% of values from the highest 28% of values. So we have P of 72 is 45 minutes, which means 72% of the wait times ever reported are less than 45 minutes. 28% of the wait times reported were more than 45 minutes. So it'd be one of the longer wait times. All right, so some notation we use is we're going to take the total number of values in the data set. K is going to represent the percentile being used. So if the percentile is 25th percentile, we'd say K is 25. L we call as our locator. This gives the position of a value. The 12th value in the list, we'd say L is 12, whatever value in the list it is. And then we have P sub K. So this just tells us what percentile we're in. So P sub 25 is another way of saying the 25th percentile. Right. So here's a little chart of what we're going to be doing. First, we want to sort the data. It's always easiest if we have lowest to highest. Okay. So if we want to compute L, we do K divided by 100 times N, where N is the number of values, K is the percentile in question. And then we have to ask ourselves a question. Is L a whole number? If yes, the value of the kth percentile is midway between the Lth value and the next value in the sorted set of data. So we can find P sub K by adding the Lth value and the next value and dividing the total by 2. If L is not a whole number, we're going to go straight down. We're going to change L by rounding it up to the next larger whole number. So we always round up to the next larger whole number. And the value of P sub K is the Lth value counting from the lowest. All right. Locations we use are called quartiles. Quartiles are measures of locations denoted by Q1, Q2, Q3. Each divide a set of data into 4 groups. So the quartiles might think there should be 4 here, but we don't have anything that represents 0 or 100. So it's just those points in the middle, even though we're separating it into 4 groups. So the first quartile is anything from 0 to 25% of the data. The second quartile, which since it's in the middle, we also are known as the median. So we normally don't say second quartile, you just say median. It would be 50% of the data, whatever that location is. So the point in the middle. And the third quartile would be the 75th percentile, whatever's that value in the list. So we think of quartiles and the median as a number in the list. So we take 25% of the data. When we arrive to that next value, that's our first quartile. The number in the middle, that's our median. And then the number where 75% of the data is to the left, 25% of the data is bigger, that's our third quartile. So some common statistics you might see. We're not going to go into too much detail here, but these are some that are commonly used in statistical tests or papers. We have the interquartile range, which means anything that falls between the third quartile minus the first quartile, we just subtract those numbers. So let's say the third quartile data value is 75. The first quartile data was 25. So remember, there's only one number for these. It's just wherever in the list that position is. You subtract them. So if it was 75 and 25, the IQR would be 50. We want to do the semi-interquartile range. We take those two values, and then we divide by 2. So if in the third quartile position, that number subtracted from the first quartile position, we divide by 2. Mid-quartile is the same thing. Instead of subtracting it to find the difference, we're just adding them together and dividing by 2. And then another common one is the 10/90th percentile range. We take whatever values. The 90th percentile, we take whatever values. The 10th percentile, and go ahead and subtract those. So the key thing just to remember here is these are numbers in a list. If you do the first quartile, you go through 25% of the list, stop at that number, that's Q1. Median we know is the number in the middle. Q3, we go through 75% of the data. Whatever that number is after we go through 75% of the list, that's Q3. And then same thing for 90 and 10. We break everything into 1% groups. 90% of the data, once we go through 90% of the data in our list, we stop at that number. That'd be 90th. 10, we go through 10% of the data. Whatever number we're at, that would be P10. All right, so something we'll use commonly with technology, we'll get what's called the 5-number summary. So the 5-number summary consists of these 5 values. So it always has the min and maximum value, and then our 3 quartiles. And remember, Q2 is the median. Right. And so we defined all of these things, so we could define what a box plot is. A box plot is a graph of a data set that consists of a line extending from the min and maximum value. And then we're going to create a box from Q1, Q2, and Q3. So that's where we're going to draw 3 lines. So the box is really Q1 to Q3. And then there'll be a line in that middle of the box where the median is. So to create a box plot, we find the 5-number summary, which we'll learn too how to find from technology. We make a line from the minimum value to the maximum value. Draw a box from Q1 to Q3, and then a line in the middle of the box for the median. So here are some examples. So if we have a skewed distribution, like the first one, the minimum value reported is 21. The maximum value is 80. And this tells us Q1 is 28, Q3 is 41, and our median is 33. So it gives us a lot more information, or a little bit easier to read using this box plot. And we can see if it's skewed, our box should be skewed in the direction it's skewed. Okay? So we still have a long tail. So that's where the tail is on our histogram as well. For a normal distribution, our box should be right in the middle. Min value 42, max value 70. We draw our box at Q1 and Q3, which is 51 and 60, and then our median would be 55. And then remember, uniform distribution, all the numbers are almost the same. Our min and max are 0 and 9. Our Q1 and Q3 would be 2 and 7. In our median, we draw the line at 5. So these blue boxes show us our Q1 and Q3. The black line in the middle of the box is the median. And then the line segment, the endpoints are the min and max. So the box plot is a nice way to draw our 5-number summary. Right. So let's talk about what's called a modified box plot and identifying outliers. So what we're going to do is we're going to find our 3 quartiles. We're going to find the IQR. So we take the value of Q3 minus the value of Q1. And we want to do 1.5 times the IQR. In a modified box plot, a data value is an outlier if it is above Q3 by 1.5 times the IQR, or below Q1 by an amount greater than 1.5 times the IQR. So another way of looking to see if something's one of those extreme values or an outlier. So to define the modified box plot, we're going to construct just a regular box plot just with a couple of modifications. So we use a special symbol to represent an outlier. So if the min or maximum value is an outlier, instead of drawing the line segment all the way out there, we're just going to put a star, and our minimum value will start at the first value that is not an outlier. So this solid horizontal line extends only to the minimum or maximum values of the data set, which exclude the outliers. All right. Have a great day, everyone. Next time we'll start talking about probability.